So our next speaker is Jordi Blasco. I've known Jordi for a number of years, particularly when he was working at the National eScience infrastructure in New Zealand. He has about 13 years of experience in HPC in various roles, everything from application development to DevOps to systems rollout. He's currently working for HPC Now. That's a company him and some colleagues formed about 6 years ago. He's going to talk about some of his activities in benchmarking and monitoring, and going to talk about some tools that they've developed. Jordi.
Okay. Thank you so much. Can you hear me well? Okay. So thank you for the introduction, and thank you for HPC Advisory Council for the invitation, and POSI for organizing this event as well. So I'm going to talk about how to identify opportunities to improve efficiency in HPC clusters. So a similar job that NCI have already conducted and have already introduced here, but more focus on the metrics that can allow job profiling real time. So that's the beauty of that. So I'm going to quickly introduce HPC Now. So HPC Now is a global HPC company. We have a scientific and also generic IT, HPC IT background. So we don't sell hardware. We only provide services and solutions on top of the hardware. And probably the thing that best defines our company is user-oriented. Okay, half of the team is computational scientist. The other half it's IT engineer. Okay, and we have a lot of background, a lot of experience in HPC from large national HPC facilities, from a researcher point of view, delivering trainings and so on in the university and the educational world, and also in the industry. And here is the quick summary on the different places that every single one of the team have already worked in, either as a user, as a researcher, as an end user support, as a sysadmin. Okay, and probably you may know some of those international. So the team is quite short, so we are just 10 people, but we don't have junior staff in the team. So as Mark said, most of us have between 15, 16 years of experience in HPC, and in addition to that, we have a lot of reputation in the HPC community because of the involvement in those projects, either in the open source community or in the PRAISE and European projects, HScale projects as well. So here's a summary on what we are providing. It's consulting for several companies, installation, remote administration, support, not only for the sysadmins, HPC sysadmins, but also scientific support for the user community and some of the companies, and also training. So this is kind of a X-ray of the company. You will quickly identify companies like Pfizer, where we are providing ongoing support for HPC, either in the scientific support and also in the sysadmin. In this part of the world, probably those companies are not very familiar. For example, Idiada is a company that has around 2,500 engineers in automotive world, so they are running simulations for major car companies, car vendor companies like Mercedes, Volkswagen, Audi, Ferrari, Lexus, and so on. So they run those simulations for bank crash, pedestrians in terms of AI, in autonomous driving, and Boston Supercomputing Center. It's one of our clients, but we also partnership with them in European projects as well. Alba, it's a synchrotron, so it's kind of a lot of stuff and very big projects that were involved already. These days we are installing probably the biggest BZFS in the King Abdullah University of Technology. So this is There's a quick summary on the motivation about why we want to identify those opportunities in the efficiency, trying to improve the efficiency in the HPC clusters. So when you procure a new cluster, the expectations is the day before, the day after you open the cluster into production, the cluster to be 100% all the time till the very end of the lifetime of the cluster, without any delays, without waiting queue for the users, okay? But that's very far from the reality. So at some point you will face what you procured at that time. Over the time, it's not getting the right expectations, so that's why a refresh platform is required every now and then. And when you are facing cluster contention, or when you are if you are taking too long in the refreshment and the hardware support or the software support is no longer there, you may have less resources available for the users. And the I/O patterns that you were thinking at the very beginning are no longer there. So you have new challenges, new users that have new challenges for the ISO system that you have. And at the end, you may experiment some higher waiting times and a high risk of user unsatisfaction, right? So what can we do to mitigate this risk? So easy, buy a cluster. Okay, you're running out of capacity, buy a new cluster. We know that you need money to do that. The refreshment cycle usually takes more or less, and it's not something that you can mitigate right away when you face the problem, right? So another option is to extend the current capacity using the cloud. So we have already done that thing for some clients. Actually, if your workload, the shape of your workload actually looks like this, cloud bursting, it's the best solution for you. So you could own an ongoing on-premise capacity, and then you only burn the peaks of needs in the cloud. And the other way to do it is by improving the efficiency and the performance. So in terms of investment, here you have to invest the whole lot and in one go, and potentially ongoing support expenses over the lifetime of the machine. Here you pay as you go, and here you have to invest in hiring really good talent to address this issue. Okay, so how to improve and how to find those opportunities is quite easy. So the magic here is that if you are able to improve the performance, you are able to improve the efficiency. And this example, we are talking about 40%. And if you are able to achieve that, somehow you are creating new resources. You are creating new allocation capacity for new jobs, either for the user that is underutilizing the resources, to other users that are sharing the facility with those potential users. So how to identify these tuning opportunities easily? That's the challenge, okay? So if you are considering traditional tools like Ganglia, so probably it's not the best way to identify those issues. It's usually based on load monitoring. There's no link to a user, there's no link to a job. You cannot see resources allocated over the cluster for that same job. And definitely there's no information about the efficiency. Okay. So what we have done already is to have a monitoring, efficiency monitoring at the job level that can review the resources requested versus the resources used. This have been key in order to identify potential issues or mistakes of user in the workflow, in the job, applications that are not able to scale to a certain limit. And when you are usually in traditional HPC environments, when you want to review the efficiency monitoring, the efficiency in the jobs, you have to wait till the job is completed, to review the efficiency, right? The desire here is to have not only a proactive job profiling, but real-time monitoring in order to trigger actions when it's required. So the idea is to infer kind of AI to take decisions for you and to to suspend some jobs, to kill some jobs when something is definitely really, really wrong. And the resolution is at this time 30 seconds, which is more or less okay for most of the HPC workloads. Okay. And 5 cents about the architecture. Architecture, we rely on big data technology. We rely on Elasticsearch and Grafana to represent the metrics. And this is the traditional pipeline, which works more or less okay, but on bigger and large HPC facilities, we find that it's not good enough. Okay, so we remove part of the access log server, log stash, and so on, and we just customize a piece of code that actually injects data into a custom data modeling into the Elasticsearch, and finally we represent the data. And the prototype that we're working now in partnership with other institutions, it relies on a custom CollectD plugin, and the Slurm Elasticsearch plugin developed in the Barcelona Supercomputing Center to inject this data again with a custom data modeling in the Elasticsearch and representing this data again in the Grafana. So the difference between the standard and the custom, so in terms of average size per package, it's 2,000 to 400, so this has a very big impact in the long-term storage for this monitoring tool, just for the efficiency. In the prototype, we are going to move from the 8 metrics to 318 metrics, and we are going to go down to 10 seconds of resolution. So the scalability at this point with a single server of Elasticsearch, which is not the ideal solution, okay, it's 50,000 nodes. Okay, so it's quite a reasonable size cluster. In a production-ready system, you need at least 3 Elasticsearch, ideally 5. Okay, so you have to multiply this for 3, and then you have the size of the cluster in theoretical limits. Okay, so in the prototype involved, you have what we have already done, and what is left is what we are working now in a partnership with other institutions as well. Most of the code it's developed by us, and a lot of institutions are very keen to try out the prototype, or they are just running the one that I showed before. Okay, so if you need to scale up because the system that you have it's much bigger than 45,000 nodes, then this very simple way to scale up. Just use 10 gig. Just use buffers to scale up to 1 order of magnitude, or just add more Elasticsearch nodes, which usually it's the right way to do it in order to increase not only the performance, but also the reliability of the whole solution. To the point, at this point, what we have already done so far in the prototype and in the solution that we have in production, and some institutions didn't show up any penalty at all in the performance based on standard HPL. So this is how it looks like. Okay. In this particular case, this is a specific institution that has around 6,000 cores, so it's more or less modest cluster. Okay. And this is kind of a behavior that we have seen. This line here represents the user request, the overall user request. In green, the actual usage. Okay, there's a mismatch between what the user community is requesting and what the user community is actually using. Based on the location, in this graph here, you have the efficiency. So it goes up to maximum value of 81%, most of the time 72%, which is really bad. Okay. In order to identify those opportunities, then we can represent the data of total CPUs under use by user. Okay. Here we print all the users, and we see that this particular user here that we have tried to anonymize. So most of the time, in average, it's wasting a lot, something around 626 CPUs over 1 week. Okay, you have an aggregated view here, and it's CPU core hours. Well, here it's the aggregated view in years or in weeks. Okay, I know what you are thinking. So if you do the math, yeah, better don't do the math. Okay, this is have a lot of implications in terms of total cost of ownership of underused CPU per a particular set of users. Okay. Okay, case studies so far. Because we don't want to show how bad have been a particular user, what we want to highlight is the benefits of adopting this, this kind of technology, and then the ongoing improvements in terms of efficiency. What you have here is the CPU time spent once we corrected the efficiency issues. Okay? So in this case, a bad user, we moved the efficiency from 74% to 97.6, and after that, this user spent 4,200,000 core hours for running the simulations that we're running. Norca user from 18% to 27%, and we have addressed some I/O issues as well. So this R-code user, that was quite a funny one. Apparently this workflow had a rate of between 5 or 10% of the jobs failing, but not failing completely. Some of the tasks were in a data state, but still the job were running. So because it's kind of a HTC workflow, after 10,000 jobs like that, the leftovers were able to manage to populate the cluster quite a lot, and well, the runtime was around 6 hours. So imagine, so populating 6 hours doing nothing with 4 CPUs per core per job, and yep. So if you do the math, it's a massive waste of resources as well. And yeah, moving the efficiency from 100 to 500, 5 times the efficiency, and also a lot of resilience. And this is sorted by CPU time spent. In the very bottom, we have a lot of case studies here, but in the very bottom, there are situations where we have been able to improve up to 600, 700 the speed up of the code. That is not going to show here, okay? But it's not the situation. So conclusions so far, we were looking for mechanisms to improve the scalability, the performance, and the efficiency. It turned out that we also have been able to detect user mistakes really early, and we have avoided massive waste of CPU time. We have improved user workflows and improve the reliability of the system. Because I didn't mention over these slides, but we have a lot of correlation of events when you have a massive slowdown on the machine, when some potential issues with the cluster file system. You can match both situations at the same time and try to explore what kind of jobs are triggering this kind of behavior in the cluster file system, and slowing down all the jobs in the cluster as well, and mitigate the problem as well. So, and the most important thing is that we have been able to accelerate the research or the business conducted through the HPC system that you are working and improve at the end of the day the user satisfaction. As mentioned before, we are working in the prototype. This is going to be joint effort with not only with HPC Now, but other institutions as well. We are open to suggestions, we are open to collaboration, and we are part of the ETP for HPC. So as you know, in Europe, this is a very big thing, so it's around 700 million euros for HPC technologies. So the expectations is to be there once we have funding for European project in order to develop this, among other things. And if you are based in Europe, so maybe we have an opportunity to fund somehow your help as well. So that's pretty much all I have. Thank you so much.